Okay, welcome back to chapter 7. We're going to finish this up. So we left off, I talked about, proteins and how you could denature them. So when we're trying to destroy microorganisms, one of the ways we can kill them is through heat. And what high temperatures will do is they will cause this to happen: irreversible denaturation of proteins. So the fried egg example, right? You put enough heat into a microorganism, you're going to cause its proteins, namely its enzymes, to become irreversibly denatured. And that is going to kill the organism, because once it's irreversible, those proteins cannot renature and they cannot go back to their normal function. So one of the ways we use to kill or inactivate microbes is by using heat. And I want you to focus on this first statement, okay? This is really, really important. So elevated temperatures are microbicidal, meaning that high temperatures and high heat can kill bacteria, fungi, other living microorganisms. High heat can also inactivate viruses, because you're going to denature that capsid or the outer protein coat. When you lower temperatures, you're not going to denature proteins. Okay, so with super high temperatures, you can irreversibly denature proteins, and once you've done that, let me just use bacteria as an example, but realize I'm talking about protozoans and fungi and other living things as well. If you heat them up high enough and cause their proteins to irreversibly denature, you're going to kill them. Okay, so high heat is absolutely microbicidal. But if you lower the temperature, all you're going to do is slow down the rate of the reactions that are happening in the cell. Cold temperatures do not denature proteins. So the protein has its normal shape, it's totally functional, but you're just decreasing the rate, and so you slow down the growth of the microbes. So that's why we say they're microbistatic. So you're not going to kill anything by putting it in the freezer or in the refrigerator, you just slow things down. Okay, but before we get to that, let me talk about heat. And unfortunately, in this lecture, I have to use the word in the English language that I hate the most, which is moist. Ugh, gross. So once again, don't memorize any of these numbers. I just want you to see the difference, okay? So if we heat up something where we want to, sterilize it and get rid of, everything that we can in terms of microbes, if we use moist heat, which means that it's basically superheated steam, which is what an autoclave does. If we can heat it up to 121 degrees Celsius, it only has to be in there for 15 minutes and it's sterile. If we compare that to dry heat, which would basically be putting something in an oven, for example, heat it up to the same temperature, but now look how long it takes, okay? 600 minutes versus 15 minutes. So this is why the autoclave is such a great instrument to have, whether you're in a medical lab, a dental lab, in the hospital, even in, a tattoo parlor, because it's so efficient at sterilizing things that you need to, such as needles and surgical tools and, agar if we're working in the microbiology lab. Heating things up in an oven doesn't work as well, and it takes a lot longer, and it's simply because when you have steam, you're conducting that heat much better, and it's penetrating much better as well. But once again, don't get hung up on these numbers. I just wanted to show you that moist heat is much more effective than dry heat. Okay, so here are a couple of terms when we talk about using temperature to kill microorganisms. So you need to consider the how high of a temperature you want to go to, and then the length of exposure. So how long are you going to let that liquid, or whatever you're trying to disinfect or sterilize, is it going to melt if you keep it in there too long, or at a high temperature? These are things that you need to consider. Okay, so higher temperatures, you usually have to use shorter exposure times. If you use lower temperatures, you have to, keep it in there for longer. Okay, kind of common sense. So there are two terms that I want you to know, and these are used a lot, especially in the food industry. Okay, especially when you're looking at pasteurization, which is basically the disinfection of liquids that are for consumption. So thermal death time is defined as the shortest length of time required to kill all microbes at a specified temperature. So in thermal death time, you keep the temperature constant, and then you measure how long it takes for everything to be killed. Thermal death point is we want everything completely dead in 10 minutes. What temperature do we have to crank, our autoclave or our, water bath up to be able to accomplish that? So yeah, used in lots of different industries. All right, so I've been yapping a lot about the autoclave, so let's talk about what that is. So the autoclave is so efficient because not only does it have really hot steam, but it also increases the pressure. So what it does is, once you close the autoclave and turn it on, you can't open the door again because it's under pressure. So what the pressure does is it fools water into thinking that it needs to go up to 121 degrees Celsius to be able to boil, as opposed to at regular atmospheric pressure, water boils at 100 degrees Celsius. So you're fooling water into, heating basically 21 degrees higher, and you're adding that extra pressure, which basically starts to pull things apart. So this is why the autoclave will get rid of really tough things like endospores and cysts. Okay, so the key is it is steam under pressure, and that's why it is so efficient. Now, autoclaves, they're really expensive, but they end up paying for themselves in the long run, simply because they're so efficient, and they end up not only doing what you need to do to get things sterilized, but also they're so efficient in terms of time because of this. Okay, so you may have seen, if you're working in a hospital or in a clinical environment, a lot of hospitals and medical facilities have an autoclave that looks like this, used to sterilize tools that are used in surgery, etc. Here was one that the typical one that I used in graduate school. You could fit a whole bunch of stuff in there. And autoclaves actually come in the size of basically an airplane fuselage. So yeah, you can fit really big stuff in there. Obviously those are, probably millions of dollars. So this is the one that's normally used in hospitals. If you work in a dental office, you may have one that's, a tabletop model, still really expensive, but very cost efficient, and they really end up paying for themselves. Now, keep in mind, you can't put living things in an autoclave. Although I know some people I would love to shove in an autoclave, but none of you guys, just so you know. But it's something that has to stand up to 121 degrees Celsius and also increase pressure. So, there are certain things that you can't put in the autoclave because they'll melt, or they'll get all warped. So you have to use different either disinfection or sterilization methods. But if you're talking scalpels, surgical saws, perfect for going in an autoclave. Then we can talk about steam where there's not pressure. Okay, once again, this is not on the exam. You don't have to know that word. And once again, don't get hung up on these numbers. I just want to show you the difference. So non-pressurized steam would be basically, you know, kind of boiling water. You know, it's not a pressure cooker, okay, like your Instant Pot. That is under pressure, okay, so that doesn't count. But you can either do 15 minutes in an autoclave, or if you want to just create some steam, you can take whatever you need to sterilize and heat it up for an hour, then let it sit for a day, then do it again for an hour, and then do this for 3 days in a row. Okay, 3 days versus 15 minutes. So once again, just shows you how efficient the autoclave is. So I had mentioned pasteurization. And yes, I do want you to know the definition of this. Pasteurization is a method used to disinfect beverages. Now note, not sterilize beverages, disinfect them. So it's usually used in the food industry and beverage industry. You want things to be safer, but you don't want to ruin the flavor and the food value. Okay, so for example, I am the queen of buying really healthy things, and then they just sit in my fridge and I don't eat them. I might as well just, if I buy salad, I might as well just throw it in the trash to begin with, because, you know, I'm going to eat a Tombstone pizza and not salad, but I digress. But let's say you bought a half gallon of milk, and then it was in the fridge, and look, you never opened it, you know, for whatever reason, you ended up not needing it. You can't go in there 6 months later and open it up and it's going to be fine, right? It's going to puff out. The milk is going to spoil. So there are microbes in there. It's not sterile, but the number of pathogens has been decreased by pasteurization. Okay, beer is the same way. Beer lasts quite a long time, but eventually if you let it sit in the garage long enough, you're going to end up with skunked beer. It's going to go bad. Okay, so pasteurization is the disinfection of beverages, not the sterilization. And really, that's what you want, okay? Can you imagine if you put milk in an autoclave, you would end up with, you know, big chunks of solid milk. Who wants to pour that in their coffee, you know, or on their cereal? So yeah, it just makes things last a little longer. So there's a couple of different methods. The flash method, you know, is 72 degrees for 15 seconds. The batch method is up to 66 degrees and it takes a lot longer, but it depends on the beverage, and, you know, you don't want things to start turning chunky. Okay, once again, don't worry about those numbers, but I do want you to know what pasteurization is. Also, pasteurization, unfortunately, is because it's disinfection and not sterilization, it's not going to get rid of organisms that have endospores, or what we call thermoduric, which means that they're really hardy, and, you know, they're not disinfected, they're not disrupted by heat. So a lot of these tend to be in the dairy case. So you'll notice if there are, you know, an outbreak of something in the dairy case, the only thing the grocery store can do is dump all that stuff in the trash, and, you know, hopefully it gets autoclaved, but, you know, there's no way to rescue it, because, you know, simple disinfection or sterilization is not going to do anything. So you probably at one point heard, you know, that there's a boil order. Okay, remember, if you boil water prior to using it to brush your teeth, or, you know, to cook or whatever, you're not sterilizing it. You are simply disinfecting it, and you are lowering the numbers of pathogens. Actually you'll hear, you know, people on the news recommending this. If you are immunocompromised, go get some sterile water. Don't even, you know, boil your water and use it, because you still may have a large number of microbes in there. But a typical boil order is, you know, you expose materials to boiling water for about 30 minutes. Great, but remember, it doesn't sterilize the water, it just disinfects it. Okay, so we talked about moist heat. Ugh, God, I hate that word. Now let's talk about dry heat. So incineration, yeah, that's super efficient. It basically is cremation. The best example of this is your little tabletop incinerator, which you guys used, which I referred to in lab as basically it's a bacterial crematorium. So yeah, if you turn things, obliterate them and heat them up to the point where they're simply ashes and dust, yeah, you're going to get rid of everything. That's sterilization. However, that's not really useful for stuff that you want to, have around for a while and to be able to use. So, cremation, yep, it's useful in terms of medical waste, cremation of bodies, but, great, but it doesn't apply to a lot of materials, especially if you need to reuse them. But yeah, that's one example of dry heat that you can do sterilization. When we talk about heating things up in a dry oven, if you want to simply disinfect, then you crank your oven up to 180 degrees Celsius and put whatever you need in there for 2 to 4 hours. But this is reserved for things that can't go in the autoclave, basically, okay? It's not the preferred method. So bottom line with heat, moist heat is always better. And the autoclave is the best because it is steam under pressure. So I talked about how, lowering temperatures makes things, bacteria static. So the important statement here, cold will not kill microbes unless maybe it's a thermophile that just, can't handle even normal temperatures. So what you're doing is you're simply slowing the rate of the reactions down. But then once you bring that material back up to room temperature, those bacteria, which are mesophiles, are going to be off to the races. And in fact, we do this in microlab. So the 10 cultures that you guys used for the bacterial unknown, every fall, we get they look like little frozen, like soup packets, like, the Lipton soup mix. And what they are just freeze-dried cultures, but they're not dead. The minute you put them into room temperature liquid broth, they start growing like crazy. So all you've done is basically stopped growth, but you haven't killed them. There are 2 different terms that deal with that. So desiccation is simply letting cultures dry out at room temperature. Think of, if you had an agar plate that had a bunch of bacterial colonies on it, and then, you just let it sit out and the agar gets all dried and crunchy. The microbes, aren't going to be dead. They're just going to be kind of sitting there dormant. That's what desiccation is. Lyophilization is a fancy word for freeze drying. And like I said, this is a great way to preserve microorganisms. Once you get them freeze dried, then, they're potentially viable forever. They're just dormant. Okay, so ultraviolet radiation. So once again, this is not used to sterilize items. It is used for disinfections. So it's used in hospital rooms. And in fact, some hospitals have a mobile UV light disinfecting machine called, I believe it's a robot. It's called Trudy, that kind of cruises around and shines UV light. Certainly helps with disinfection. Also used in operating rooms, food prep areas, dental offices. We also use this in the crime lab. Before we would start a case, we would turn our UV light on in the place that we were going to process evidence. And the goal was to try to, kind of ruin any, potential contaminating DNA that would be there. It's also very commonly used in water treatment. So when you choose a chemical, and this goes back to the list of how chemicals work and, what makes things ideal. A lot of this is common sense, okay? We would love it to be able to be diluted and have it work in really low concentrations, because that means that it's going to cost less, and it's going to be a little safer. We want it to be soluble in water or alcohol, and once it's diluted, to be able to last a long time. We would love for it to just attack microbes and kill them without being toxic to human and animal tissues. Okay, that's kind of a tough goal, but that's what we're going for. It has to be able to penetrate inanimate surfaces to a sufficient degree. We don't want it to have to be, you know, resistant by if you have a lot of XX cells. We want it to work really strong. Be great if it didn't eat through, you know, whatever we're trying to use as a disinfectant. We don't want it to smell bad, and we need it to be available and to not cost $1 million. So, I mean, that's kind of the dream list. Hopefully you tick some of these boxes, but once again, you're probably not going to hit all of them, unfortunately. We're going to see this repeated in chapter 20, and it actually becomes even harder because you're talking about drugs that are actually going into our bodies. So here are the things that affect how well these chemicals work. The nature of the microorganism just means, you know, is it bacteria? Is it a virus? Is it, you know, endospores? The nature of the material, is it a liquid? Is it a solid? Can it stand up to being autoclaved? How many cells do we have? How much time do we have to be able to treat it? And also what the chemical is actually doing. Germicide just is a general term that just, germ just means like we're talking about anything, bacteria, viruses, whatever. So I want to finish up, and I think, yeah, oh, goody, we only have 2 slides left, yay. So heavy metal compounds, okay? So these have been used in the past. In fact, in the news, the Reverend Jim Baker was just arrested in Missouri because he was peddling a silver solution as a cure to COVID-19, which is completely unproven and false. And newsflash, it's dangerous for humans to consume heavy metals. Okay, mercury, gold, silver, zinc. Yep, they've been used. The problem is that they are very toxic to humans. Okay, you can also be allergic to heavy metals, but these often cause liver and kidney damage. So yeah, we really don't want to consume them. You can also, you know, with body fluids or, you know, waste products, you can neutralize them anyway. What they normally do is they attach to proteins and enzymes and inactivate them. But guess what? We ourselves also have proteins and enzymes that can be inactivated by these heavy metal compounds. One of the best examples, if you remember way back in chapter 1, when I mentioned Paul Ehrlich, who invented the drug Salvarsan, which you know, theoretically cured syphilis, that drug was arsenic derived. And so awesome, your syphilis is gone, but guess what? Now you're gonna die of either liver or kidney damage because it was a heavy metal. So yeah, very dangerous. If you're dealing with just microbes on an agar plate or an inanimate surface, then yeah, you know, potentially you could use them, but really, you know, mercury and gold are the only ones that still have significance. But just to show you what this looks like, so here is a plate, okay, and there's bacteria growing all over it. Here we put a little hunk of silver. Here we put a little hunk of gold, and you can see what we refer to as zones of inhibition, which are clear. So what that means is that there's something in the silver and the gold that is either inhibiting or killing the bacteria because it's not able to grow near to the metal. Okay, but once again, I just want to, you know, emphasize not good for human or animal consumption because it's going to be very toxic to our liver and our kidneys. Yay! We're done with chapter 7.